introduce Dr. Sarthak Chandra, who is in MIT right now, and he's a former student of IIT Kanpur, and he was a star student, as was everybody else here, including not just the speakers, but also the audience. So I hope you all inspire each other. Then he did his PhD from the University of Maryland, and then he did a postdoctoral under the guidance of Professor Ed Ott and Professor Michelle. How do you pronounce her name?
Girvan. Michelle Girvan.
Michelle Girvan. Okay. I never get it right, but okay, now I know. And now he's working at MIT with Professor Ila Fiete, and he's going to speak on, he's working on problems which are related to the emergence and advantages of modularity in neural circuits. And also, as anybody who has worked in Maryland, he's an expert on dynamical systems. So let's see how these come together in his application to reservoir computing. So Sarthak, maybe you can share your slides.
Okay, yeah. Thanks for the introduction, and thanks for inviting me to speak here. Very honored to be able to speak, present at IIT Madras, even though it's remotely for now. Hopefully, at some point in the future, that will be in person as well. But okay, so let me quickly go to slideshow mode. Hopefully, you all can see my slides. So I'm going to be talking about. I'll be more sticking almost entirely to reservoir computing very specifically throughout my talk. And I'm going to be talking about basically what happens when you try to do reservoir computing in like a noisy real world setting, right? So, and I'll primarily looking at two problems. One is of network inference, which is going to relate very, very closely to the talk we just heard, and to the question of dynamical noise. So I'm glad everyone has stuck around until the end over here, and I'm also happy to be put at the end because a lot of the background that I'm going to end up using has been very nicely covered by some very wonderful speakers earlier in the session itself. So what I'm going to be talking about today is basically been in collaboration with these people. There's grad student Amitabh Banerjee from University of Maryland and professors Brian Hunt, Raj Roy, and Ed Ott, all at University of Maryland. So quick outline of my talk. This is going to relate very directly. The first part is going to relate very directly to what Aditi was talking about. So I'm going to be talking about using reservoir computing for network inference. And in particular, this is also going to be a form of interventional causality, I believe. And in particular, though, I'm going to spend time thinking about application of these techniques towards calcium fluorescence data from C. elegans and what are the interesting intricacies that pop up over there. I will talk about how you actually come to some statistical significance of some evaluated networks. And then after that, I'll talk about reservoir computing in the presence of dynamical noise and how it actually works with a dynamical noise filter. So, okay, with that, let me just get right into it. You all have probably heard lots of introductions to reservoir computing by this point. But all I want to say over here is basically there are lots of flavors of reservoir computing that one could potentially use. And I'm just going to be using the simple one-step prediction setup for like the entirety of my talk, where basically what I'm saying is that if I'm given some data stream x of t, I'm basically going to be just feeding that into my reservoir over some training phase. And in my training phase, I basically want to try to train the reservoir to output x of t plus 1. And then in a testing phase, potentially I can go to like a closed loop system and I can make the reservoir just take inputs, its own output prediction, and then just run as an autonomous dynamical system. Right, so it's a very simple one-step prediction setup for the reservoir that we're going to be using. And just to be a bit more precise, I'm going to use the kind of idea where this is in a nice computational model. I think Professor Manish Shimali had basically described this kind of a setting earlier in his talk. But basically, just think of x of t as your input signal, which is projected onto your reservoir nodes via some input matrix, and there's some nonlinear coupling and dynamical system that goes on over here. And basically, then you're training this readout matrix W out to try to basically have x of t plus 1 be W out times R of t plus 1. So basically, you're optimizing your output weight matrix to try to get this one-time step prediction. And in the classical reservoir framework, we're not really going to touch any of the other weights. And generally we're going to be thinking of doing this output weight matrix optimization through some sort of loss like this. Is just a quadratic loss, and basically you can do this with some sort of regression term to come to an evaluation of what W out is. And then in the testing phase over here, basically you just take your X prime as your prediction of W out times R, and you feed that back into your reservoir, and now you're again going as this autonomous system. So, okay, so this is a simple one-step prediction setup of reservoir computing. And as we've seen so many times in this workshop already, it's super useful when particularly looking at time series data that's coming from dynamical systems, right? And there are all sorts of different tasks you can look at. Chaotic time series prediction is something that I think was talked about earlier as well, and something I will be getting to later in my talk. But the first part, I'm going to focus on the task of network inference, or in other words, basically what is causality detection of nodes on a network, right? And so this is something that people from my group back at University of Maryland have looked at in the past. And so I'm basically going to be building on what was described in these papers earlier in the particular context of real world data. So what exactly is this network inference task, right? So given some amount of data coming from some n nodes, so you have n time series, x1 of t, x2 of t, all the way up to xn of t. They're basically coming from some nodes. And underlying this data time series is some network that is actually governing the dynamics of the system. And so the task of network inference is basically, given these set of time series, how do you actually infer what are the set of network connections? Or basically, given these time series, can you infer some sense of which nodes causally affect which nodes, right? What are the directional links in the system? And as I said earlier, we're basically going to focus on this particular case of taking neuronal activity from this particular organism. So this is C. elegans. This is not to scale image unless you're seeing my presentation on a really small device. It's around 1 mm. It's a small worm like creature. And it's a very, very common model organism for several studies. And the reason for that is basically, at least in the context of neuroscience, one of the important reasons why it is a model organism is that the entire connectome has been mapped out, right? So there are 302 neurons in total. And if you use a technique like calcium fluorescence imaging, you can actually allow for almost whole organism imaging simultaneously. But of course, that does have the con that calcium fluorescence imaging is generally low temporal resolution. And so it's kind of a trade-off where you have low temporal resolution data, but you really have data for a very large number of neurons measured simultaneously. And so one thing I do want to point out over here that's going to actually become more crucial later in my talk is that I want to note over here particularly that neurons themselves are more complex than just a single variable, right? They're not just characterized by a single scalar variable. They are more complex internal dynamics. There are ion channels, there are different ions, and there's you can write out cable theory. You can do all sorts of things to talk about neural dynamics. But over here, this data measurement system is really collapsing all that information into a single observable fluorescence intensity, right? So there is a lot of loss of information in that sense. And this is actually going to be relevant to what I'm going to talk about later. So to give you a feel of what this data looks like, basically we have like a bunch of time series that look like this, right? And so basically the color is talking about the intensity of this calcium fluorescence signal. And what you can basically see is that, okay, the resolution is not that great. And, this is like the length of the one session of recording that you can take from this worm. Also, what I'd like to point out over here, as you can see, that there are some neurons that are much more active than other neurons. The active neurons generally tend to be the motor neurons in the system because these are recordings taken as this worm is basically moving about. And so the motor neurons tend to be far more active than the other neurons in the network. And for that reason, we're just going to largely restrict our interest to just looking at the motor neurons because, there's just not enough signal in the other neuron activities. So we're just going to look at data coming from motor neurons. And there's also a left-right symmetry in this worm. And so at the end of the day, we're going to talk about trying to infer this particular complicated network of 8 nodes, given calcium fluorescence imaging data. Right, so this is the task that we're basically going to try to address today through reservoir computing for network inference, right? So let me actually tell you a little bit about exactly how do reservoir computers perform network inference first. And then we'll actually get to what happens when you start throwing C elegans data into this particularly. So, okay, so what is the kind of inference we want to do, right? So basically, if you have this kind of a network, as the previous speaker very helpfully explained, that you have different forms of causal inference that you could talk about. And one effective form of causal inference might be this interventional kind of causal inference, where I might say that if I have access to this network, I can go ahead and directly perturb, say, one node. So let's say I perturb node x1, right? Then what I can see is that if I perturb node x1, which nodes get can you see perturbations propagate to? So in this case, for example, once I perturb node x1, I can see that my perturbations have propagated to this node x2 and this other node over here. And so then I can say with potentially some confidence that these two links exist in my network, right? So basically, if you have this kind of an access to the network where you can go about perturbing these nodes, then you have some sense of being able to estimate a causal effect of one node on another. But of course, the whole game over here is that we want to be able to do this non-invasively. Given only access to data, we still want to, in some sense, be able to tell the effect of perturbing one node and evaluating how these perturbations are propagating through the network, right? And that would be a sense of causal inference. And so basically, how do we do this? Well, given the theme of this workshop, we basically get reservoir computers to the rescue here. So what you can basically do is, as I was saying earlier, that if you train a reservoir computer as, a one-time step predictor, then the reservoir in itself becomes like a proxy for this original system, right? Because now when you go to closed loop, it runs an autonomous system, which is really just a proxy of this original system. So now what I can do is I can take my reservoir computer, I can feed in data from all of these n nodes, and I can train it to output the one-time step prediction of all of these n nodes. Now, if my reservoir computer is a proxy of this original dynamical system, then instead of perturbing nodes in my actual network, I can just perturb nodes in my reservoir computer proxy. So I can now take my reservoir computer proxy of the system, I can now perturb x1 over here, and I can see which nodes over here get perturbed, and to which nodes are these perturbations spreading. And mathematically speaking, this ends up just falling out to evaluating like the Jacobian of this learned map and averaging that for the time series. But essentially what you're basically doing is you can estimate the strength of perturbation spreading to various nodes. And so what we basically do is that we use that to assign a score for each possible edge, which is basically just going to be the magnitude of this Jacobian that's looking at the transformation from node I to node J, right? And so that gives you a score associated with the possible edge. And then what you would expect is that indeed, if say node 2 is causally dependent on node 1, then the Jacobian term corresponding to node 1 pointing to node 2 is going to have a large value, right? And so we said, okay, let's do this for like a toy model. So we just hooked up a bunch of Lorentz oscillators. This is just the classic Lorentz 63 model. We just hooked up a bunch of them in a network, just coupled the y variables to the x variables, and then just ran the network of Lorentz oscillators, got the data, fed that into the reservoir, and saw, okay, what scores do we get if we try to calculate these Jacobian values, right? And so if you basically look at a distribution of scores that you obtain, you get something that looks like this, right? So as I was saying earlier, what you might expect is that large scores probably correspond to what are actual causal connections in my data, what are actual links in my network, whereas small scores are essentially going to correspond to things that are probably not causally linked and are not, not connected by network edges in this graph, right? And indeed, that's what ends up being the case. So if you now put a threshold and you say that, oh, I'm going to call everything to the right as a link in my network, that ends up corresponding to exactly what the actual ground truth is. So indeed, everything above this threshold are actual links, and everything below this threshold are actually not links. So the orange and blue are the ground truth distributions of what are the links and the non-links. Okay, so this seems wonderful, right? I mean, okay, so we seem to have a method that does causal inference, and it seems to work wonderfully on this problem. But actually, this is a very, very idealized scenario, right? I started off with this very nice toy model of Lorentz oscillator, something we're all familiar with, and we got this very nice separation in this distribution. We're like, okay, this is how we do link inference. In practice, that's not really how it ends up working out. In practice, what basically ends up happening is that you get much more, just one blob of a distribution. You don't really end up getting something that splits itself in two. So what did we basically do to get this distribution over here? We basically said that, okay, we saw that in C elegans and in real world systems, often you just have a partial measurement of system dynamics. So over here also, let's take the Lorentz oscillators connector and network again. But instead of measuring the entire nodal state at every node, we're just going to observe a single variable from each node that corresponds to some sort of combined variable across of this entire three-dimensional network's Lorentz state. So the only variable that you observe from each node in this case is the basically x1 square by the average value of x square plus y1 square plus average value of y square plus z square divided by the average value of z square. So just this one combined statistic. So now when you try to do link inference on this partial measurement data, you actually get this distribution that looks like this. And in this case, there's no real good choice of where you can put your threshold, right? Because there's no clear gap in my distribution. And so the question we basically want to try to understand is, okay, in a case that is like this, how would you actually go about performing link inference? How would you actually go about ascertaining what actually might be a link and what actually might not be a link, right? Because, when you actually peer into this distribution, you can actually see that the distribution of scores for pairs of nodes that are actually links and the distribution of scores for pairs of nodes that are not actually links are actually just merging completely into each other, right? And so, where do you actually end up putting the threshold? You can say maybe you want to put a threshold here where, I'm going to say that I only want links. So I'm going to put my threshold over here so that I only get links. Or you can say, maybe I'm okay with being more risky. I want more links, but I'm also okay with a few non-links, in which case you might put the threshold over here. So really, you can only do all of this and actually talk about how many links you want to get and how much certainty do you want with your links if you actually knew what the distributions of the link scores and the distribution of the non-link scores were separately. But of course, when you're actually doing the experiment, this is all you see. You just see this one black distribution, and you have no idea where the link score distribution starts and where the non-link score distribution starts, right? And I must say that, I had set this problem up in the context of using this Lorentz oscillator model and this combined observed variable. But indeed, if you actually look at C elegans, calcium fluorescence data as well, you get a distribution that looks like this as well. Now, you might say that, hey, over here, the distributions do seem to have kind of split up, and maybe this cluster over here at the rightmost edge are links, or maybe these two clusters are links. But actually, if you peer into it, you can see that the links go all the way to a much, much smaller value of scores as well. And only then do the non-links start. So ideally, we would want to know how do we actually manage to ascertain where we should put a threshold to try to understand what is a link and what is not a link, even after having done all of this score estimation on this causal inference problem. Okay, so how do we actually go about addressing this problem, right? So what we basically do is we're going to construct what's called a causality destroyed surrogate data. So surrogate data is, surrogate methods are basically methods that are quite often when you're interested in a statistical inference problem like this. And the basic goal of surrogate data is to try to come up with some other method to approximate the data distribution that you're interested in. So over here, basically what I'm going to basically claim is that I'm going to present to you a surrogate data generation method that, particularly for the case of reservoir computing based link inference, the causality destroyed surrogate data ends up following the same distribution as the non-link scores. Okay, so how exactly does this work out, right? So let's say that you have this set of nodes again, and now each node over here has with it associated some time series, right? And so if I'm interested in, say, this first node for now, associated with this node, I can follow this entire, pipeline that I've described for you earlier, where I just feed it to a reservoir, make predictions, and calculate Jacobian values, right? So I can feed it to this pipeline, I get all these score values. And as we were saying earlier, these score values can potentially just be the single blob of a distribution. And what you want to infer is which of these are links and which of these are non-links, right? So what we basically propose as a surrogate data generation method is we say, okay, let's take a copy of this entire system, and we're just going to shift one of the time series. So if you're interested in the first node, I'm just going to shift the first time series by some large value. So now what you would expect is that if there were any causal inference-based signatures in the two time series, they would basically all get destroyed, because we're only thinking of causal inference over a small number of time steps, because you expect perturbations to propagate slowly through the network. So once you shift time series by a large amount, you basically destroyed any sense of causality in the network. Now you have these much more long time correlations. And so now if you now shift this time series and now evaluate a set of scores, what we basically hypothesized is that the set of scores that you now obtain is going to be very similar to the set of scores which don't actually correspond to any links in your system, right? All we're saying is that now that you've destroyed the causality by shifting this time series, the score that you'll obtain is going to be as if there was no causality to start off with, right? And so this is basically the hypothesis that we have, that the surrogate data distribution, surrogate score distribution that you obtain after performing the shift of time series is basically going to correspond to this non-link score distribution that we wanted to inference to start off, right? And indeed, that does appear to be the case. So if we go back to this distribution case for C elegans that we were looking at earlier, if I now plot what the surrogate data distribution looks like, you can see it really matches quite well with the non-link score distribution. And this plot is starting to get a little noisy, so let's just clear it up a bit. So basically, you can see quite clearly over here that the non-link score distribution and the surrogate score distribution basically overlap exactly onto each other. And so indeed, this shift does seem to have been a good way. And I know it's a little hard to infer this directly just from looking at a noisy histogram like this. So another potential way you could, compare these two distributions is to just plot like the cumulative distribution function of both of these PDFs. And so basically, if you plot one of the CDF versus the other, you can see this almost perfectly fits on y equal to x line. Once again, really demonstrating that these distributions are indeed quite identical. And so basically what that tells you is that you have a close agreement between the surrogate and the non-link score distributions. And so this picture that I was describing for you just a moment ago does indeed seem to hold. And so now that you have this, now you can actually use my surrogate to try to estimate, okay, given access only to my black distribution, if I pick a particular score, what is the probability that it came from a non-link score? Or basically, what is the probability that came from the surrogate score distribution? Or what is the probability that actually came from an actual link score or the rest of this black distribution? And so really, you can now start using the surrogate data distribution or the surrogate score distribution to start obtaining p-values and statistical significances associated with different choice of thresholds. And indeed, we can actually go ahead and do that in the C elegans network. And we can now say that, okay, as you change the different thresholds, you can get a different number of true positives and a different number of false positives. And the number of true positives and false positives that you get matches with the p-value that you want, that you are comfortable with. So you can now choose to put a threshold that will give you a p-value of say 0.1. And now you can, reliably get, in this case, roughly 10 links and maybe one false positive link, right? So indeed, you are actually obtaining a good statistical significance of whatever link inference you manage to achieve with your data. And I do want to quickly say that, I've posed this problem as basically saying that this is largely just because of the partial measurement that's happening in the system. And indeed, that is definitely a very, very important reason as to why my distributions merged and this did start to be a problem in the first case. But there are a lot of other factors as well that do contribute to when link score distributions and non-link score distributions tend to merge. And this relates to length of time series and temporal resolution and all sorts of factors like this. I won't really have time to get into that right now. Happy to talk about that more after the talk. But at a very high level, it does appear that the evaluating surrogate score distributions using causality destroyed surrogate data seems to work in all of the other cases as well. And so you can really reliably use reservoir computing not only to do this causal inference problem, but also associate statistical significance with indeed what was a link and what was not a link in your obtained solution of this inference problem. Okay, but really, when I've described all this, this should be one question that's popping into your mind that I've kind of brushed underneath the rug, which is that why even should a reservoir computer work with a system like C. elegans, right? A trained reservoir computer, after all, is a deterministic dynamical system, right? In the reservoir computer, in the framework that I proposed, there is no noise term, so to say, right? It's an entirely deterministic system. Whereas we know that, if you're actually looking at a worm moving about, it's not entirely deterministic, right? Neurons themselves are subject to various Poisson or spike fluctuations. There are thermal fluctuations that actually start getting relevant at this scale of the neurons in C. elegans. And so all sorts of other factors that are not really deterministic. So why would a reservoir possibly work, right? Because a reservoir computer is clearly not learning the map that corresponds to the true neural dynamics, because there is no deterministic map. And so more generally, this leads to the question that I'm going to try to address in the remainder of my talk, which is just more generally, how do reservoir computers work with noisy data, right? What can you actually do if the data that you're trying to train on is going to be noisy, right? How do reservoir computers actually deal with that? And so that's basically going to be what is going to be the focus of the second part of my talk, where basically I'm interested in talking about reservoir computing in the presence of dynamical noise, right? So, noise is certainly pervasive in systems at all sorts of scales, right? We know any experiment you're ever going to do is going to have some form of noise, right? And it really corrupts real-world systems at all sorts of scales, right? Whether you're doing really small experimental measurements where you have little quantum fluctuations that are stochastic and you can't really predict them apart from in a distributional sense. And if you're measuring very large systems, then you start talking about, you want to try modeling something like, like some very large chaotic system, maybe the weather or something like that. Then you have completely unpredictable high-dimensional chaos that starts affecting the system at smaller scales, which starts propagating to these larger scales. So once again, even over there, you have some form of noise that's really corrupting the system. So now we've seen that reservoir computers seem to work in these noisy environments. And so the question that I'm going to try to answer here first is, can reservoir computers filter out this noise and obtain a noise-free signal, right? Now, why you might be interested in this, I hope is something, I hope I don't have to spend too much effort trying to convince why you might want to get rid of noise. But basically, the high-level idea is, if you are only measuring data streams that are riddled with noise, really trying to come to any understanding of the underlying physics can be extremely, extremely tricky. If somehow we can access a clean version of the system, which does not have any noise in it, then that can actually allow for building of physical models. It can actually allow for some sort of analysis. It can actually allow for some sort of inference. So basically, if you can figure out some method to obtain clean data from your noisy data, then it really allows you to get much further ahead in your task of understanding what's going on in this problem, right? And so what we ideally want is a general purpose noise filter that doesn't require access to the clean data and works irrespective of the type or form of noise. Because as we've seen, noise can come in a variety of ways, and you may not even know what really the source of noise is in your particular experiment. And so what I'm basically going to propose is that reservoir computing works as this general purpose noise filter. Now, I want to be even more specific, that when you're talking about noise, you could in principle have different types of noise, right? So one example is observational noise, right? So in observational noise, basically you have this problem where you have some system dynamics, x dot is equal to, say, f of x. And your observation is basically some y is equal to x plus some noise term, some observational noise term. Now, this problem is far more well studied because it's actually an easier problem, right? So over here, the true trajectory or the clean system's trajectory is always near your observed trajectory. So if you observe some trajectory that looks like this, you can infer that there's actually some clean trajectory and there's some noise that's added on top of this. And this gets harder when the noise starts having statistics and spectra that are similar to your data. But indeed, you can still often do it, right? You can do various spectral methods. You can use independent component analysis. You can use some sort of Kalman filtering. You can use low-S. You can use all sorts of different methods when you have observational noise. And that's simply kind of because your true trajectory is always kind of close by, So some kind of filtering, some kind of temporally local transformation will generally get you there. Now, dynamical noise, however, is a completely different beast. In this case, if your true system dynamics is x dot is equal to f of x, your noisy system dynamics is now x dot is equal to f of x comma noise, right? And f can in general be some nonlinear function that's coupling both x and noise. And the observation that we're going to assume over here is now just x. So for simplicity, we're not going to assume that we have observational noise on top of this dynamical noise. Let's just talk about dynamical noise for now, because that itself is a pretty hard problem. Because in this case, because of this continuous stochastic forcing that's coming from this noise input, the trajectory doesn't even remain close to the true dynamics. So for example, this blue curve over here is just a time series of the x variable of the Lorentz 1963 model. If I now inject this with noise, in particular, this is Ornstein-Uhlenbeck noise, you can get time series that look something like this, right? And you can see this is drastically different from the time series you started off with. The black curve is nowhere close to the blue curve in any sense. It spends these it can spend these really long times about unstable fixed points because of some sort of noise-induced stabilization, which can really make the system appear very, very different. And so the task that I want to try to solve with the Reservoir computer is now given access to only this black data, this black curve. Can I actually reconstruct this blue curve, right? And now I should say, of course, that trying to, in some sense, extract a true trajectory is going to be meaningless. So I can't really talk about obtaining a true trajectory in the sense of having minimum least square error or something like that, because this trajectory that I'm observing is being continuously forced by the stochastic perturbation. So what you can estimate is going to be the true dynamics in the sense of a climate, right? I'm using climate in the sense of weather modeling in terms of statistical information related to your time series. So you can maybe talk about the measure of the attractor. You can maybe talk about the distribution of the attractor when projected onto various subspaces. You can talk about maybe the power spectrum of your time series. And basically try to measure various quantities. And when we're talking about trying to uncover a clean system, it can only really be in this sense. It can only really be clean in the sense of having the right attractor, clean in the sense of having the right power spectrum. It can't really be clean in the sense of having a low least squares with respect to your data, right? Okay, now, yeah, so what kinds of forms of coupling can there be, right? In general, this F could be a very general form of coupling. The primary consideration that I'll talk about for most of the talk, for most of the next 10-15 minutes, is basically a system where if I set the noise term to 0, it's equivalent to taking an ensemble average over my noise, right? Now, of course, this doesn't have to be true. For example, if my coupled dynamics was F plus the square of my noise signal, for example, then indeed the ensemble average or the average is basically going to be the clean system plus some sort of bias, right? Whereas when I set the noise to 0, I would have just the clean system. So in general, f of x comma 0 does not have to be the same as the averaged or as the ensemble average of f of x comma xi. But primarily, let's start off by considering cases where this is the case, right? So we're just going to start off with very simple kind of noise couplings. Now, the punchline basically of this talk is going to be that reservoir computing in the usual prediction framework, in the usual one-time step prediction framework, automatically filters dynamical noise. So what I'm basically going to show is that if I just use the same framework that I started off with, if I feed in this dynamical noise-laden trajectory, and I train my reservoir computer for one-time step prediction of this noisy trajectory, and then go to the closed loop in the testing phase, the autonomous reservoir computer will spontaneously be like the clean dynamical system without the dynamical noise, and it will automatically filter out the dynamical noise. So let me just justify this for you first with some numerical examples, and then time permits, maybe I'll tell a little bit about some theory about why this might be the case. So let's say we have this is my true system, just your usual Lorentz attractor. This point cloud over here is basically showing the attractor projected down onto a plane. In this case, my time series looks something like this. My power spectrum looks something like this. And this is the distribution projected onto the x variable. So let's just use these quantities to try to see what my reservoir computer does, right? This will be my climate estimates. So now when I inject noise into my system, and in particular in this case, I'm going to be injecting colored noise, not just white noise. I'm going to inject colored noise, which also has its own time scale, which is going to be similar to the time scale of the Lorentz attractor itself. In this case, you can see that the time series looks completely different. The power spectrum has also smoothened out completely, and my distribution has qualitatively changed. I have gone from a 3-peak distribution to a 2-peak distribution because of some sort of noise stabilization that happens near the unstable fixed points. And so now, given access to only this black data, what happens in the reservoir closed loop output? Turns out, over here, this is the noise spectrum, which you can see also has time scales similar to the underlying data system as well. It turns out that if you just feed this to a reservoir and put it on the closed loop framework without having to worry about anything else really, the reservoir in the closed loop will give you a system that looks exactly like the clean system. You can see the time series once again looks qualitatively like a Lorentz attractor time series. The distributions match basically perfectly. You can see the red dashed curve is exactly on top of this blue curve. And really, this works remarkably well, even from very large deviations away from the original attractor. So over here, I basically have the same setup where now this input noise is again colored noise with just a much, much longer time scale, which really introduces this long-term stabilization of these trajectories. So you can see over here, the autocorrelation of the black data time series or noisy system is much, much larger than the underlying true system. Note that the x-axis on a log scale over here. If it wasn't on a log scale, the difference is even more drastic. But the true system and the reservoir output match exactly with each other. Right. So despite only having access to the noisy system, the reservoir seems to be able to completely clean up the dynamical noise and present a clean system in its output. Now, yeah, and you can see this even this distribution over here. The data distribution is very sharp peaks, these unstable fixed points, but the reservoir can completely filter out that noise. Okay, so why in the world does this work, right? Why should a reservoir filter dynamical noise? Now, it turns out this is very interesting, and the analysis actually ends up depending on the time scale of the noise. So first, let's talk about white noise and talk about why should a reservoir computer filter out white noise? Now, the essential idea boils down to the fact that W out, the output matrix that you compute in reservoir computing in the framework that I described earlier, was just through linear regression. And as we know, when you're generally doing linear regression, if I add noise to my linear regression, I still get a good fit, right? My linear regression can still average through noise. And in a sense, that's what the reservoir computer does as well. So let's assume that, so this is like my true dynamics and my system dynamics. Let me just write this out as a map just for, mathematical simplicity to explain the argument out. So now let's assume that my dynamical system looks as x of t plus delta t is some clean map plus this noise term, right? And this clean map I'm going to define as x sub c of t plus delta t, right? So the reservoir dynamics, as I said earlier, basically you have r of t plus delta t is some nonlinear function of the input matrix projecting onto x and the reservoir state at the previous time step, right? So notably, as you can see from this equation, r of t only depends on x at previous time steps, right? Basically because r of t plus delta t is only a function of x of t. And basically what that means that because x of t basically depends on xi at the previous time, what that tells you is that the reservoir time state at time t only depends on the noise time state to delta t back, right? And crucially, it does not depend on the noise time series 1 delta t ago. And so with just this observation, if you now write out the term that we actually try to minimize in computing W out, right? If I just expand x of t as being x sub c plus this noise term, right? And you can just do some simple algebra to argue out that the only relevant term in the loss evaluation is the first term, which is W out times R minus x sub c of t, because the average value of xi is a constant and this term goes to 0 because we're assuming that xi has an average value of 0. And so because this is the only term that you're basically computing a loss against, it's effectively like learning the map from x to x sub c, right? Because the noise term just doesn't contribute. And so training the reservoir through linear regression basically results in learning a map from x of t minus delta t to x sub c of t. and not x of t. And so indeed, we're directly learning the clean map just by virtue of the method of linear regressions that is utilized in reservoir computing to estimate these out matrices. Okay, now notice you note that this argument only very strictly works for white noise, because if my noise was colored, if my noise had temporal autocorrelation, then this statement would not be true. Then the noise at one time step would depend at noise at previous time steps, right? So this argument strictly works only for the case of white noise. But as I showed you earlier, it does seem to work for colored noise as well, right? So why should a reservoir filter out colored noise? So that you can explain by virtue of the fact that you can think of colored noise itself as a dynamical system that's forced by white noise, right? So if I think of Ornstein-Uhlenbeck noise, for example, you can write out a dynamical system for the noise as basically being like a decaying term plus a term that's forced by noise, right? So this is just basically trying to write out, like Langevin equations for an Ornstein-Uhlenbeck process. And basically, my entire dynamical system coupled with the colored noise now starts looking like this coupled system. So I have x dot is equal to f sub c plus xi, and xi dot is some minus alpha xi plus a white noise term, right? So now I have a coupled system which is forced by white noise. Now, following what I said earlier, reservoir computers can filter white noise, which basically means that if I can get rid of this white noise term and I get this system instead. And now the xi equation over here, as you can basically see, just decays to 0, just xi dot is minus alpha xi. And so the net system asymptotically just approaches x dot is equal to f sub c of x. So the net system, even though it was driven by colored noise, ends up just approaching the clean system, just because of the fact that you could clean out white noise earlier. So in fact, let me quickly show you that this is indeed a good representation of what the reservoir computer is doing. So what you can do is, you can take the reservoir computer and just as a hypothetical, instead of just trying to predict the next time step of the time series, you can maybe also try to predict the next time step of the noise, assuming you had some hypothetical access to what the noise time series looked like. Now, if I close the loop, I can ask, what does xi look like? What does a closed loop output of xi look like? If our argument is correct, the closed loop output of xi should correspond to this right set of equations, and we should see xi decaying. And indeed, that's exactly what we see, right? Now, this is just a few different random runs. And you can see it's quite noisy. But if you actually average out over multiple runs, then indeed the average reservoir reconstruction of the noise variable is an exponential decay curve that would exactly match what you would theoretically expect from the correlation timescale of the Ornstein-Uhlenbeck noise. Right? So indeed, this picture of saying that the white noise is ignored is a good representation of how the reservoir computer is able to filter out dynamical noise. Now, one thing interesting to point out over here is that this means that the mechanism for removal of white noise and colored noise is distinct. White noise was removed through an averaging process through linear regression, whereas colored noise was removed by setting the noise term to 0, right? So now if I go back to a system like this, right, where setting the noise term to 0 is different from averaging the system, then what should I get, right? This analysis basically tells me that I could either get the clean system defined as setting the noise term to 0, or I could get the average system defined as taking the ensemble average of this coupled f. And which one you should get should end up depending on the time scale of the noise. So basically the theory suggests that for fast time scale noise, the average f would be learned. And in the case of colored noise with slower time scale, the clean system would be learned. Now, the very interesting thing over here is that when I'm talking about fast and slow, I need to describe what this is relative to, right? And it turns out that this is basically relative to the reservoir time step. So if I have noise of a given time scale and I can flexibly change my reservoir time step, I can make this noise appear as fast and evaluate the clean system, or I can make this noise appear as slow and evaluate the clean system, whichever one might be to the task that you're particularly trying to solve, and whatever might correspond better to your prescribed notion of what a clean system might be underlying the stochastically driven system. And indeed, that is what we see even numerically. So over here now I have an even more complicated system where my noise term has a quadratic term, so it has a non-zero mean, and it is also in the form of a multiplicative term. So it's not just a just an additive term anymore. And indeed, we see in this case that when the noise timescale is much, much larger than the reservoir timescale, then I obtain something that looks like the clean system. Now, I know it's hard to see over here, so let's just zoom in. You can see that indeed the reservoir output matches the clean system and is distinct from the average system, right? And you can see the average system basically is asymmetric simply because I have this bias term that is non-zero when averaged. And when I go to noise timescales that are comparable to reservoir timescales, or alternatively, if I increase my reservoir timescale, decrease my reservoir timescale to be of the order of the noise timescales, then my reservoir output starts matching the average system. And in between these two different regions, you basically get something that interpolates between these two choices. So basically, in a system like this, there's no obvious answer of what does it mean to filter out dynamical noise. But what we're basically saying is that dependent on what you think the right answer is, you can really use your reservoir to obtain that correct answer and really, filter out dynamical noise even when the data distribution of the training data looks completely different. I mean, you can see the black curves look nothing like the red or the blue, but the reservoir computer is very reliably able to just filter all of this out. So basically, yeah, so reservoir computers seem to be able to reconstruct an underlying deterministic dynamical system behavior, even in the presence of very large dynamical noise. As you can see, the attractor can be drastically different. Which system is reconstructed does end up depending on the noise timescale. For fast timescale, we have an average system. For slow timescale, we have a clean system. And there is a subtlety here that I haven't really got into it. Be happy to talk about this more after the talk. Is that, I talked about turning off the white noise term, but strictly speaking, that is also not a unique process. And that ends up depending on your favorite interpretation of stochastic partial differential equations, right? And this comes down to Ito versus Stratanovich conventions and so on and so forth. And so turning off the white noise term is not unique, but it turns out the reservoir has to make a particular choice. And that ends up being a well-defined choice that I'm happy to talk more about later. But potentially this might explain why reservoir computers seem to work for link inference, even the stochastic real-world systems such as elegans and other real-world problems that people use the reservoir computers for, simply because reservoir computers actually filter out dynamical noise, even though your attractor may no longer look anything like your clean system attractor. So yeah, so to conclude, RCs are pretty good for link inference. When you're unsure of what your link inference means, we actually have a proposed method to quantitatively assess statistical certainty of this link inference. And reservoir computers are just supremely effective at filtering out white and color dynamical noise. And crucially, they just start filtering out this noise even when just used in the usual configuration of time series prediction. So you don't even have to do something extra. It might already be happening in your data and you don't realize it. With that, I'd like to thank you. And this is my email ID in case people want to shoot me with any questions after the talk. But I'm absolutely happy to take questions right now.
Thank you, Sarthak. Questions?
See, there's something in the chat, I see. Nothing.
Yeah. There is something in the chat, but that actually wants videos and stuff like that. But I have a question. See, if you can do all this for certain kinds of dynamical systems, which are essentially stable, well-defined attractors. Say, for example, if you had a system which undergoes a crisis or something which has something like unstable dimension variability, this would not work, right?
Yes. So I should point out, I mean, I do agree. So if basically, when I'm talking about, maybe this is a good figure over here. And basically, when I'm adding my stochastic perturbation, definitely my attractor I'm far away from the actual attractor, but crucially, the trajectories that I take are still intersecting my original attractor.
Right.
So if I had a system that was on the brink of a crisis or on the brink of a phase transition, and my noise pushed you into a regime that was nowhere close to my original system attractor, then this would not work. And then you'd start inferring something relevant to that other basin that you're lying in.
Right. So this would work wherever the shadowing theorems work, isn't it?
Essentially, yes. I think that's right. I'm unclear about. Okay, so shadowing theorem in itself, I think, strictly applies in a very restricted set of systems. You need hyperbolic and and whatnot. But qualitatively, yes. Qualitatively, I agree. Qualitatively, where you expect shadowing to hold, where you expect your trajectories to be intersecting your original attractor, they're expected to work. But I mean, definitely, I do want to point out that, when you start looking at trajectories like this, the trajectories are not really close to the attractor, not really following the flow of the attractor, but they are, within some ball of the attractor.
Yeah. And see, would unstable periodic orbits play any role?
So I think that is in some sense what you're kind of seeing over here. So particularly in this one system, this fixed point over here that is originally an unstable fixed point. When you start injecting noise to it, it can start appearing like a stable fixed point, right?
It stabilizes
stable
the
periodic
unstable.
orbit.
Okay.
Exactly. Now it turns out that doesn't seem to be an issue for the reservoir, right? Even when I insert time series that looks like this, which is spending really long amounts of time in these near these unstable periodic orbits, that doesn't really seem to bother the reservoir and can still extract of the clean system. In fact, if I just go to these distributions over here, you can see how much time it's spending near these unstable fixed points, just pretty large fraction of the time. But the reservoir seems to be very reliably able to extract of the clean underlying system.
Okay. Will it work for mixed phase-space systems? Let's say where you actually have, let's take, these are clean dissipative systems, right? Suppose you take a Hamiltonian system where your phase space is nicely mixed and where you start really makes a difference to how your trajectory behaves. So then what do you expect to happen?
That is a good question. We haven't really done any tests, particularly in that case. I think qualitatively, I think the theory holds as long as I think as long as you're densely sampling some open set around what you're ergodically sampling what you would call ergodically sampling a neighborhood of what you would call the clean system. I think you're good to go.
Okay.
I think the theory holds generally without making any additional assumptions on what F looks like.
Okay.
Or F sub C looks like.
Yeah. Well, that's nice to know.
We haven't actually done the numerical test, but that's my hypothesis. That's my guess, at least.
Yeah. Anybody else?
Sarthak. Just to clarify, with respect to the causality diagram that you were showing earlier there, if we were to do you consider cases where you're augmenting the causality on being perturbed?
No. So in particular, this entire analysis is done directly from just this entire analysis that we do is entirely just from this calcium fluorescence data from C. elegans. And the particular task over here was just this worm was just moving around foraging for food or something. So there's no actual perturbations going on in this network in the data that was sampled. And similarly for what we do with these toy models with Lorentz oscillator as well, we just run the dynamical system and get data. We don't actually augment it by actually going in and perturbing the system.
No, the reason I was asking augmentation here is because you mentioned about surrogate data models. So that was the line of thought that I had. Perhaps, you are trying to bring in dynamic causality as well.
Right. So our goal was to try to, in effect, arrive at dynamic causality, but without actually having to do any perturbations. So when we set up this surrogate also, we do it in a way by which we don't ever have to actually go in and invasively do anything to our system, but just playing around with the data that we've collected, we try to construct the surrogate data distributions.
Okay. And the other question that I actually had was, when you are actually using a surrogate data and you're trying, and you are mixing it with the original data here, how do you differentiate between a noise and a nonlinearity in a data?
How do I distinguish between noise and nonlinearity in the data? I'm not entirely sure I follow. I mean, basically, yeah. Could you explain a little bit more about what you mean by that?
Sure. See, in cases where you have a dynamical system, you tend to have your data evolving over time, as a consequence of which there could be certain deviations or differences that could actually appear in the original data. So how do you differentiate such type of nonlinearities and differences? And how do you differentiate, how do you differentiate that from whether it belongs to the category of a noise, or is it a nonlinear?
Yeah, right. So the goal, okay. So I guess there's a two-part answer to that question, right? The first part is that the goal of trying to set up a surrogate and trying to use the data, the distributions you get from the surrogate, is basically to try to prescribe what probabilities do you think, what do you think the probability is that a score that you got has arrived because at this, say you got some low score value. What is the probability that you got this low score value because of the noise in your data that didn't allow you to estimate your link well, or because of the nonlinearity in the system, which is making it harder for you to actually estimate the link inference, right? And so one of the goals of trying to set up a surrogate data distribution is really to be able to estimate what the probability is of it being in either of the two classes without actually knowing for sure which of the two classes it is in. But the second part of the answer is also that when you have noise in the data, it turns out to not affect the reservoir so much. So it tends to not be too much of a problem. So particularly, we're basically writing this up in a paper. It should appear in PNAS soon. Where basically we do examine, the effect of injecting noise and, in different forms as well, into how that affects the quality of your link inference and how that affects the quality of your surrogate and so on. And it does turn out that this entire method is largely robust to injection of noise, unless the noise starts getting very large. So it doesn't tend to be a problem. But where it is a problem, we're hoping the surrogate can help us get some insight into what is really a link and what is just noise appearing as a link, or vice versa.
I understand. Yeah. Thank you.
Yeah.
Sarthak, yeah. So can I ask a question?
Yeah, absolutely. Yeah.
Yeah. Very, very nice work, Sarthak. I was just trying to, this is just a very basic question probably. Like, is there a way to understand the reservoir through these embedding theorems? I mean, is it realizing some embedding, and hence it's not really, that mysterious? I'm just trying to understand from, say, witness immersion theorem, or is there a way to realize that realizing some kind of an embedding and hence we're able to reconstruct it? Again, I don't know. It's just a very basic question. Is there some material on this, or you can throw some light if you know?
Okay. So yes, there are definitely relationships. I can point you to a paper as well, which I could maybe send it to you in chat or send it to you by email or something. Great. But basically, there's a paper by my group at University of Maryland. I'm not on that paper, but some of the other. In fact, I think Jaideep is also not on that paper actually. But okay, there's paper basically try to talk about that, what reservoir computing is basically doing by virtue of this nonlinear, recurrent system, is essentially just coming up with high dimensional embeddings of your data, right? And what Tarkin's embedding or the other embedding theorems are basically saying is that if you take your data and if you embed it in a high dimension in this temporal way, by taking these time multiplexing, then you obtain a good representation of your attractor. So what the reservoir is basically doing is that it already has a history, right? It has memory by virtue of recurrence, right? So it has access to previous time points as well, but only in the form of a very nonlinear function of the current time and previous time points, right? And so basically it's just like a very high dimensional nonlinear projection of the system state and previous history of the system state. And which then you might say, yeah, of course, then it's going to start looking like a system attractor just because of, embedding like results. And so there is some work that people have tried to do in this direction. I can point you towards that.
Yeah, because these embedding theorems give like say greater than 2n, and so I don't know whether reservoir is projecting to a really high dimension, and can we reduce it further? That's probably the optimality of the reservoir maybe, and things of that nature, right? I would imagine.
Absolutely,
how can the reservoir
so,
be, and
Right. So I think the two things to think about in that context. The first thing is that in the reservoir, you've pushed to this high dimensional projection, but at the end of the day, you're also only doing a linear readout.
True.
Right. Now, when I'm doing like an embedding, I can do like a nonlinear readout of where the next time step go, right? Now, by virtue of saying that I only want to do a linear readout, I actually end up having to go to a much higher dimensional system to try to, separate points.
Got it. Okay.
Typical classification people think of, you go to a high dimensions just so that you can start separating points out. So in that sense, you do need to start going to a high dimensional system. But there has been work in the direction of where, you take a large reservoir that trains on a system, and then you start asking the question of which nodes can you start knocking out, and how many nodes can you start knocking out before you start getting loss in performance. So there are some people who have addressed that, but to the best of my understanding, I don't think there's any theoretical work that has been done in this direction about how good you can do or how small can your reservoirs be. To the best of my understanding, all the results are only if it's big enough, then it will work.
Thank you. That's very useful. Yeah.
So, anyone? So let us thank Sarthak. That was a very interesting talk, and I can clearly see that it has started many directions of thought for many people. So let's hope this talk will start off some collaborations. That would be really nice.
I would love that. Yes.
Yeah. And thank you so much for taking all the trouble and being such an enthusiastic participants. In fact, I would like to thank all of you today who have spoken today, plus all the people who spoke yesterday, for coming, participating in our workshop and presenting such clear and informative talks. So on behalf of CCHD, let me thank all of you, and we would like to invite you to come and visit us the next time you are around, so that you actually come and meet all of us and see what kind of work we are doing, and let's see how things go from there. So I am stopping here, and I'd like to hand over to Sayan just to close. Sayan, are you there?
Ma'am, he's not here actually.
Oh, he's not there. Okay, then yeah. I'll close. Rohan, why don't you close? You've done all the hard work. Close.
Okay. All right. So thank you very much, everybody. We've had a great 2-day session, and been fortunate enough to help organize this event, along with, of course, Lima ma'am and Sayan sir and Srinivasa. And actually, we have had enthusiastic participants from all over, especially in our institute. We have had participants from different departments who have taken interest in reservoir computing. And I hope that helps increase the usage of it, at least in our labs and wherever computational work is going on. With that, I would like to thank everybody who joined today and yesterday, and for help making it a huge success, I would say, especially after the discussions that we've taken place. So thank you very much, ma'am. Thank you very much, everybody, for participating enthusiastically.